Right. So I'm going to suppress my audio. I think it's working. All right, gentlemen, welcome. Okay, so I kind of give me just a moment. I'll be right back. Just a moment. All right. So let's see. As far as announcements go, so let me see. I've got my confirmation. It looks like my screen is recording. Again, I did my augmentation where, I started streaming before I let you guys in. I'm thinking that its inability to stream has something to do with the number of people in the room or whatever. So I think if I do that first, then it seems like it works a little better. Let me see. I think our exam one was due last night at midnight. With any assignment, I still have people asking for extensions. So with any assignment, all of our assignments have a natural extension built into them, even though they have due dates. The due dates, if you want to earn, the due dates are there if you want to earn over a 90%, right? So you submit the assignment on time, you potentially could earn over 90. But if you submit it late, you can earn up to 90%, right? So, with all assignments, we get unlimited attempts, and the system is set to take your highest score. Okay, so so you don't have to ask for an extension. Just do your best. It's already in there for every assignment. The only assignment that really doesn't have an extension is the final exam, because once the final exam is due, the semester's over. All right. So exam one should have covered chapter 1 and chapter 2. I'm pretty sure. Did you guys have any questions you wanted to talk about before we kind of start chapter 3? Okay, so as always, if you have questions, just feel free to unmute yourself to get my attention, and we can talk about it. But I'm just going to kind of press forward.
Professor?
Yes.
This is Christopher Walker. I contacted you in an email. I want to say either this past Sunday or a week ago, in regards to just getting the access to my math lab.
Have you been trying to use the book voucher?
Yes.
And has it come in?
Mm-mm.
It still hasn't come in?
No.
Did the bookstore say anything about it?
No, not really, because I did through Pearson. It was I signed up for the Pearson Plus subscription.
Oh, you paid directly to Pearson?
Yes.
How did you access it? Just kind of walk me through what you did to access it.
So you just search for Pearson Plus, and it's basically a monthly subscription. Mm-hmm.
I would say try to get a refund from that. And what you do to access it, You go to Blackboard. You go to
Okay.
Blackboard. You go to it's a folder. It's like folder number 3 that says assignments. You click on that, and then the very first link says My Math Lab All Assignments. When you click on that link, that's going to put you where you need to be, and that's what you want to purchase access to. Because I think
Okay.
that whatever you may have bought may have been something that we're not using.
Okay.
Yeah. So they should give you a refund. And again, just go to Blackboard, go to All Assignments, and that's going to put you where you need to be. And then purchase that one.
Okay. Thank you.
Okay. All right. That was a good one. Any other questions? Other ones? Yeah. So, yeah, and like Pearson does have like a whole slew of like different stuff. So that's that. Because of that is why I linked it to Blackboard, because yeah, it's like if you type the wrong thing and get access to the wrong thing, then you're not going to find what you're looking for. Okay. So I can't think of anything else. So chapter 3. Let's move into chapter 3. And so the goal for today, our schedule, our rate is still a little bit ambitious. We're still on track to be doing about 2 sections a day. So the first half of class we'll spend on 3.1 today, and then the second half is 3.2 as best we can. As usual, whatever we don't finish together, I do expect you to, watch my pre-recorded lectures. Okay, no, let's go like this. I don't know why it does this every time I start right here. Okay, that's better. Okay. So chapter 3, so hopefully we have some level of familiarity with differentiation, right? Long story short, the derivative is the slope of the tangent line at a point on a curve, right? So you can use the derivative to find the equation of the tangent line. And we saw several like techniques for finding the derivative. We introduced derivative with the limit definition, the limit of the difference quotient definition. Remember, there's this long drawn out thing, and I was like, guys, don't worry. I feel we have some shortcuts that are coming. All this long stuff that we're doing, you're going to be able to look at it and spit out the answer, right? So then shortly after that limit definition, we started working through some of the theorems and the properties and some of the techniques for finding derivative, from like, bringing the power down, all that jazz, right? So power, and then, sum and difference rule, product rule, quotient rule, all that kind of jazz. So now we want to take those techniques for finding derivative, and we want to start to explore some applications of the derivative, okay? So in section 3.1, the first application that we want to focus on is using first derivatives to find max and min values and sketch the graph, right? So again, if you don't remember anything else, the main thing I do want you to kind of keep on the forefront when talking about derivatives, the derivative is just the slope of the tangent line at a point. From there, I think you can kind of there's a logical flow. I think you can handle the rest from there. Okay, so there's some objectives here. First, we like to find relative extrema of continuous functions using the first derivative test, and then sketch the graph of continuous functions, right? So let me kind of preface it by like a brief summary. So when we're talking about maxima and minima, if we're looking at a graph, all the maxima is like the peak of a mountain. So our graphs have all these curves, it's curving up and curving down. So now we're going to start to see how we can use the derivative to start sketching these graphs. And so right now we're going to focus on the peaks of the mountains, and the minima are the bottom of the valley, right? So we have these definitions. It says this. Let's go. And I'll check attendance for the second wave in just about 3 minutes. Oh, I forgot about you. I always forget about my pen until I go to use it. I had to let it charge for a little bit. So I'll just read this for now. It says a function f is increasing over an interval if for every a and b in the interval I, if a is less than b, then f of a is less than f of b. So that's just the definition of a function increasing. Generally, that's over an open interval. Then whenever you have 2 different x values where a is strictly less than b, then the corresponding y's follow the same order, right? Then f of a is less than f of b. So as long as that's true for all the corresponding x's on an open interval, then we say that the function is increasing. Long story short, when you're looking at the graph, as you trace it left to right, that means that the function is increasing. It's going up, right? If the input value A is less than the input B, then the output for A is less than the output for B, right? So it just matches. That's okay. We say a function f is decreasing over an open interval I if for every A and B on the interval, if A is less than B, then f of A is greater than f of B, right? So basically what this is saying is pictorially, as we trace the graph from the left to right, our graph is going to go down, right? So that's from college algebra. If the input A is less than the input B, then the output for A is greater than the output for B, right? So it's just, they have a reciprocal relationship. Okay. All right, so let's let that be. So we have this first theorem. Let f be differentiable over an open interval I. Then if f prime, in other words, the slope of the tangent line is positive for all x on the open interval I, then f is increasing over I. Okay, so we have a curve. We have this interval where we're kind of focused on the curve. So then, yeah, it's okay. Man, she hears us. Hey, I need you to stop. Come here. Come on. So given a differentiable function and we kind of consider it over some interval, whenever the derivative is positive for all x on our interval, then we say that the function is increasing, right? So now we have this correlation between the derivative and a function increasing. So whenever the first derivative is positive, that means the function is increasing. If the first derivative is negative over an interval, then we say that f is decreasing. Okay. All right, let's keep going. So we've talked about functions increasing and then decreasing. So now we can start to talk about what do we mean by critical value. A critical value of a function f is any number c in the domain of f for which the tangent line at c f of c is horizontal or for which the derivative does not exist, right? So where the tangent line is horizontal or does not exist, let's focus on the one where the tangent line is horizontal. That's basically going to be either the top of the peak of your mountain or the bottom of the valley, right? That's where the function goes from increasing to decreasing, or where the function goes from decreasing to increasing. If the first derivative is undefined or does not exist, we say that's a critical value. It's not necessarily going to be the peak of a mountain or the bottom of a valley. Okay. So if c is a critical value, if we say that c is a critical value if f of c exists and f prime of c equals 0, right? So okay, so it looks like there are times when f of c exists, but f prime of c does not exist. So that could still be a critical value. We'll address this as it arises in different cases. If c is a critical value of the function f, then f of c is a critical point, all right? So I feel like this will make more sense as we kind of work some examples. But the idea here is that given the curve, right, we're trying to pinpoint, either the peak of the mountain or the bottom of the valley. The peak of the mountain, we usually call that the local maxima, and then the bottom of the valley, we call that the local minimum. And again, the idea is those usually exist where a function goes from increasing to decreasing, or it goes from decreasing to increasing, respectively. Okay, more definitions. Okay, let me go through this one. Let the open interval I be in the domain of f, then f of c is a relative min if there's an open interval I containing c such that f of c is less than or equal to all f of x for all x on the open interval I, right? So we have a curve. We say that this point is going to be the minimum value if that f of c is less than all nearby y values, right? And the relative max is a similar discussion. We say that f of c is going to be a max if it's greater than all nearby y values on this open interval I, right? Again, I know it's a lot of like jargon. This is just kind of setting the stage. I feel like when we start looking at images and working examples, it'll become more clear. I'm trying to finish these theorems before I do the attendance. If a function f has a relative extreme value, f of c on an open interval, then c is a critical value and f prime of c is 0 or f prime of c does not exist, all right? So for the critical values, we identify the critical values when f of c exists and when either f prime of c is 0 or f prime of c does not exist, right? So basically what we're going to be doing is finding the derivative, set it to 0 and solve, and then interpret the results and interpret what they mean. But the first derivative tells us whether a function is increasing or decreasing, all right? That's what it's telling us, okay. Geez, these are not stopping. Okay, let me check on you guys in Zoom. All right, so we got a good amount. Let's go like this. Ooh. This one. This one. This one. This one. Okay. All right, I guess that's everybody. No, see, somebody's missing their last name. I think this him. Hopefully, I shouldn't have another person with that first name, so I'm just gonna go with it. I'm gonna let him in. I'm gonna suppress this, and we're gonna hop back over here. Okay. All right. So let's see. So we have this theorem 3. If you're just joining us, we are in chapter 3, and we're working on section 3.1 that's centered around the first derivative and how it relates to our curves and our graphs. And long story short, the first derivative is telling us whether a function is increasing or decreasing over an interval, okay? So, and chapter 3 is basically focused on applications of the derivative, right? And so we're looking at applications of the first derivative with increasing and decreasing. So for any continuous function f that has exactly one critical value c in an open interval, then, okay, so this first derivative test. So it says that f has a relative min at c if f prime is negative on a to c, and f prime is positive on c to b. So basically this is saying the function is going from decreasing to increasing, right? Because when f prime is negative, that means the function is decreasing. When f prime is positive, that means the function is increasing. So if our function is going from decreasing to increasing, then f of c, that c is going to be the f of c is going to be our minimum value, right? Because the function is going from decreasing to increasing. And then we say that f has a relative max at c if f prime is positive on the left side of c and f prime is negative on the right side of c. That is, f is increasing from the left to c and decreasing to the right of c, right? So if the function goes from increasing to decreasing, then we say it's a relative relative max. And then we say that f has neither a relative max nor a relative min at c if f prime of x has the same sign on either side of c. Right. So when we take the first derivative and we evaluate it on the left of c and on the right of c, if they have the same sign, then there's no relative minimum. Okay. And so I kind of want to like summarize as far as the sign of our first derivative. I'm trying to think of how to articulate it, but it's like pretty much the sign is going to be the same across the board, but it's going to be separated by your critical values, where either f prime is 0 or f prime is undefined. So once you identify those values of x where f prime is either 0 or undefined, then what that does is breaks our number line, our x-axis, it breaks it up into segments. So then what we do is basically we test in each segment. We choose a number from the first segment, we look at the sign of the derivative. We choose a number from the second segment, look at the sign of the derivative, right? So then we're basically looking at the sign of the derivative in each of those segments, and that tells us whether the function is going from increasing to decreasing or vice versa or neither, right? Okay, that's a lot. I'm trying to get to an example so we can see it in action. Okay, right, and here's the pictorial representation. It's still not an example, but here's like a pictorial representation of what we've been discussing. I guess my pen should have enough charge to get us through class. I gotta like coddle my chihuahua so that she don't lose her mind. Okay, let's see. So it says, So the graph over the open interval from A to B, right? So the original graph for this one is like the parabola, so U-shaped curve. So if we're considering the C, so then any x that you choose from A to C, when you put it into the derivative, in this case, is going to be negative. Any x here will be positive. So this is an example of something that's going from decreasing to increasing. So then that means that C is a relative minimum value. And it's a similar discussion for this guy down here. All right. Okay. So again, I feel like this will be easier when we work an example. You know, we have our original curve. We find that this is a critical value. So then, you know, when we choose a point here, we're going to get a negative in the derivative. We choose a point here, we're going to get a negative in the derivative. So they would have the same signs, and then there's no relative max or min. All right. Okay. All right, let's keep going. Okay, let's look at this one. So here we're asked to graph the function f given by this and find the relative extrema. Okay, let me give myself some space. Let me see. It likes to throw attention when I do this, so we're gonna cross our fingers. Okay, looks pretty good. Okay, let me go to view, seamless. Let me add one more page. All right, so for something like this, now, when I'm sketching curves, let me see. I'm gonna try to summarize this as best I can. So the first thing I like to investigate, first I like to investigate my intercepts. Okay. I usually like to do the y-intercept first. So I'll say, I usually like to, because that's oftentimes easier. First I'll do my y-intercept, then I'll look for my x-intercept. Okay. Let's see. What else? I guess we can find our critical values from there. So then we could look at the first derivative. We could just say f prime of x, right? So that's going to tell us whether it's increasing, decreasing, or constant. And so from there, we're looking for our critical values. Critical values. The critical values are going to be the values where the first derivative is either 0 or undefined. So in that second step, we're looking for critical values. Okay. The third step, so once we identify our critical values, we want to choose a few additional points. So I'm just going to abbreviate it as additional points. And these points need to be between all the critical values and beyond the critical values, right? So I'll just say between and beyond. Let me kind of move this down. So this is essentially what I do every time I'm curve sketching. Few additional points, I'm going to say between and beyond all critical values. And let me think about that. Yeah, let's just do the critical values for now. That's enough for now. So yeah, right, because that's the only time it's going to change from increasing to decreasing. So we identify our critical values, choose a few points between and beyond those guys, and then the final thing is basically graph. So sketch the graph. Okay. Basically put it all together. Put it all together. Okay. So let's do a rough sketch. Let's start with what we were given and let's just walk through it. And at first it might seem a little bit overwhelming, but for the most part, it's gonna kind of be kind of repetitive. Oh, I know we're rapidly approaching the halfway point. So we have this f of x equals 2x cubed minus 3x squared minus 12x plus 12. Okay. So we want to sketch this, right? Now, there are other properties and techniques that we can invoke, but I was just trying to get like the main ones, right? So let's start with our intercepts. Okay. And then for the y-intercept, all right, you know how to find the y-intercept. What do? We set x equal to 0. So if we set x to 0 and solve, then we're going to get what? 2 times 0 cubed minus 3 times, my dogs. Stinky dog farts. Oh my goodness. I can taste it. Oh man, get out of here. Woo. It's getting worse. What are you eating? Smelly dog. Get out of here. Go. Go to bed. Ooh. Smells like grass, and I know she's not eating grass. And it's so weird because I can't smell anything else, but that somehow made it through my sinuses. I'm like, oh my goodness. We're setting x to 0, right? Let's keep going, right? So then from there, if you set x to 0, you see that you get 12, right? And we can say f of 0, okay? So when x is 0, the corresponding y is 12. So we got our y-intercept, all right? Let's highlight that. Okay, if we can find the y-intercept, then we can also talk about the x-intercept. Okay, so for the x-intercept, I might bypass it on this one. We'll try to factor it. If we don't get the factoring right away, I'm going to bypass it just for the sake of simplicity. In order to find the x-intercept, we would have to set y to 0. Sometimes this can be challenging. Let's give this one a go, right? Now we could factor out x squared, but I don't think anything lines up, right? I'm gonna actually let this one be. I'm gonna skip the x-intercept for now, just for the sake of simplicity. I'm just gonna skip it for now. Okay, we'll come back to that. Let me think. We got an s. There is at least one x-intercept. Let me think about it. Because if we factor out x squared from there, we would have what? That's going to be an x minus 1. Those aren't going to match. We could rearrange it, factor out a 2x. We would get x squared. That's not going to help anything either. Yeah, for right now, I'm just going to skip the x-intercept. I'm just going to skip it because I think it's going to make it too bad for this one. Let's keep going though. So our critical values, let's look at the first derivative. Okay. So I'm going to say f prime. So then basically what we want to do is we want to set it equal to 0 and solve, right? So let's look at the first derivative. So if we take the first derivative, 3 times 2 is what? 6x squared minus 6x minus 12, right? And we want to set that to 0 and solve. If we set this to 0 and solve, let's see, it looks like we can factor out a 6. We can divide 6 from all the terms. That'll give us x squared minus x minus 2 equals 0. Okay. X and x plus and minus a negative 2 and a positive 1. Okay. So then from there, we get that for the first derivative, our candidates for our critical values are going to be x equals negative 1 or x equals 2. All right. So that's from the first derivative, right? So then what we want to do now, we want to test to see, okay, so these x values make the first derivative 0. When the first derivative is 0, that means that the slope of our tangent line is potentially 0 at these x values. So then that's only going to occur either at the peak of a mountain or the bottom of a valley. So we want to basically do some test points, right? So here, go ahead.
How'd you get x squared minus x minus 2 equals 0?
I factored out a 6 from everything. So basically I said this divided by 6, divided by 6, divided by 6, and divided by 6. All right. Okay.
Oh, okay.
Yeah, so right here, let's do this. I mean, it's fine. Let's see. So we'll say that this is regarding f prime. So -1 makes f prime 0, and also 2 makes f prime 0. So what's your favorite number to the left of -1? Let's plug in -2. When we plug in -2 into the first derivative, this is negative, this is negative, negative times negative is positive, right? So to the left of -1, the first derivative is positive. That implies that our original function is increasing to the left of -1. Okay. Let's see what happens when we're on between -1 and 2. Your favorite number between -1 and 2, I'm gonna choose, okay, I think we did when x was 0 already. We got a positive result, so we can actually use that. So but when when x is between -1 and 2, the first derivative is going to be, sorry, should it be negative? Sorry, let me plug it in. I'm jumping the gun a little bit. Okay, so our favorite number between -1 and 2, when I plug in 0, let's see what happens. So when we plug in 0, this is positive, this is negative. A positive times a negative is negative. So what we're saying is the first derivative is negative between those two candidates. So that implies that our original function is decreasing between those two. All right. So it looks like our graph is increasing. It peaks at when x is -1. We do need to find the corresponding y. Let's see what happens. We need to verify on the right-hand side of 2. So our favorite number to the right of 2, let's choose when x is 3. Okay. So if we plug in when x is 3 into the first derivative, this is going to be positive. This is going to be positive. A positive times a positive is positive. So the first derivative is always positive on the right side of 2. All right. It's only going to change at those critical values. So that's what I was trying to say earlier. The sign of the first derivative is only going to change at those critical values. Okay. So from this is saying that, oh, we have a relative max when x is -1. And we have a relative min when x is 2. So that's a relative max. This is a relative minimum. Okay. So then we just want a few additional points. Usually I have my x-intercept. Again, I did just kind of skip it for this one. But we just a few additional points between these critical values and the x-intercept if we had it. And then basically just put them together, right? Let's just find a few additional points. So the third step, additional points. Okay. So let's see. We can do like when x is, all right, let's do, so these are going into the original, by the way. So we'll do when x is -2, find the corresponding y. Let's go ahead and do when x is -1, find the corresponding y. I think we did when x was 0 already. We got 12. We'll just include it. Okay. Let's do when x is 3. We're going to find the corresponding y. So what I'm going to use is my trusty dusty rusty. Yeah, this guy. Oh, is it not there anymore? It's okay. I'll just make a new one. This one. Okay. Reload and refresh. Okay. Then the original, I'm going to go to my y equals. We got our 2x to the power of 3 minus 3x squared minus 12x plus 12. Okay. I mean, there are other tests that we could do to find those zeros, but they might not be rational. We're just going to go with this. Okay. So we just want to find these few additional points. So whenever I want to call in a function, so to the right of the calculator is a button that says clear. Left of that button is a button that says VARS. I think that's short for variables. I'm going to click on that button. I'm going to go to the right to go to Y variables, 1 for function, and 1 again to call in a function that I just typed in. So let's verify that the first one works. When x is 0, we should get 12. Okay. So then when x is -2, let's see, we get 8. Okay. So we're just going to put 8 here. When x is -1, we get 19 for now. When x is 3, okay, we get 3. Okay. So then the final thing is to put it all together. So I'm just going to say F. Okay. I'm just going to do a rough sketch. Let's do like this. Let's go here. I think I'm going to do dots and like 2. Come on. Okay, 1 should be fine. Apply. Okay. Let me see my x's. X's look like they went from like -4 to 4 approximately, but the y's, we got 8, 19. Yeah, I get it. I know we're halfway. We need to be going to the next section. 12, 3. We don't have any negative y values anywhere. Okay. It'd be nice if we could find that negative. Probably if we went like -3 when x was -3. Let me see. When x is, let's do -3. Okay, I'll go ahead and include that one as well. So that way, now we have a sense of at least where our x-intercept is. So when x is -3, the corresponding y is -33. Okay. So my y's look like, oh no, I wasn't trying to do that. Thank you. Come on. Come on. Come on. There you go. Okay. So x is like -4 to 4, but my y is like -40 up to 20, right? Okay. So I'm just gonna make a rough sketch. Let's see. Let's go like this. Okay, this will be my positive y in this direction. We'll go about, I guess about here for my x's. Okay. This will be my positive x in this direction. Let me move this over just a smidge. That looks better. Okay. So let me see. For the x's, we said -4 to 4. So let's do like this. Let's let this be 1, 2, 3. Is 3? I think 3 is fine. And then same thing here. There's the 1, 2, 3, right? This is our origin. We said this is our 1, 2, 3, -1, -2, -3. Now the y's, maybe 40, -40 to 20. Let's see. Here we go 5, 10, 15, 20. Let's see. -5, 10, 15, 20. Let me see. 10, 20, 30. Do we want to go by 10s? Let's go by 10s instead. Hopefully that's not too big. So we'll go 10, 20, 30, 40. And we'll go -10, -20, -30, -40. Okay, just to capture the points that we found. Okay. So let's plot these points. Okay. So when x is -3, we got 33. So that's about here, -3, about here. Okay. -2 and 8. So -2, 8 is about here. So notice it's going to cross the x-axis somewhere between the -3 and -2. So our x-intercept was something irrational. That's why I skipped it. I was like, I think it's irrational because I wasn't able to factor it. So I was like, I'll come back to it. So now we have a sense of we at least know the x-intercept is somewhere between -3 and -2. Okay, when x is -1, we're at 19. So let's see here, -1, 19. 0, 12 is about here. Okay. And then over 3 and up 3 is about here. And that's the point 3 coming 3. Okay. So then the moment of truth, if we put all this together, we had a cubic function, so we're kind of anticipating a S-shaped curve. I think we said that this was a relative max right here. And I think that this was what was the other one? When x was 2. I guess we need to find the corresponding y. Okay, we need to find that when x is 2. because our critical value, right? Okay. And we said we want to do when x is 2. We get -8. Okay, that's fine. -8, okay. So then 2 -8 is about here, over 2 and down 8 is about right there. That's, oh no. I'm trying to wrap this up. This is 2 -8, and we said this was our relative minimum. Okay, who's this guy? So now if we just connect it with a smooth curve, basically we're going something like this, passing through that point, passing through our maximum value, passing through that. It's crossing somewhere over here, passing through this. They're irrational, but this was the gist of it, right? You know, and we could find those. We could do more tests to find those x-intercepts. They might not be rational, you know, but one of them might be one actually, but then the others might be irrational. Let's see. Let's do a quick test. If we go back to the original, if we let x be 1, let's see what happens. And you can use synthetic division, right, from college algebra. So if x is 1, we're going to have what? 2 minus 3 is -1. I think the corresponding y is -1, right? So it's not 0. So I think we have irrational zeros. I think the zeros are there. They're just not rational. So because they're not rational, you know, we can't factor it. But this is the gist of it, right? This is the gist. Let me do like this. Go to my paper. I just want to turn this off and apply. Okay. So we get something like this. So now that was us sketching it by hand. I'm going to wrap this up. Single page, right? So this is the work that we did. Again, a quick recap. We did our intercepts. Again, my recommendation is at least start with the y-intercept. So you see, we weren't able to find a clean x-intercept. They are there, but it was too much, so we just skipped it for now. Then we looked at the first derivative, and that gave us candidates for our critical values. Once we found those critical values, then we needed to do our test. We need to do our first derivative test to see how does the first derivative behave on either side of those critical values. If the first derivative were positive, that means our original function was increasing. If our first derivative was negative, that means our original function was decreasing. And you can see it here. The original function is increasing. The original function is decreasing. Original function is increasing, right? So after the first derivative test, then we found a few additional points between our critical values and our x-intercepts and beyond, all right? So basically what we're saying is we found a few points here, here, and here, right? And then once we had all those ordered pairs, we plotted them and then connected everything with a smooth curve, okay? Let's see, and we should have a typed version of what we just did. Let's see. Okay. Okay, let's see. So it says we can now see some features of the graph, find a general expression for the derivative. Okay, so we did this. So determine where f prime does not exist or where it's 0. Since it's a polynomial, it's nowhere, it's not going to exist. So only the possibilities of critical values where the derivative is 0. Okay. So then we got 2 or -1. These two critical values partition the number line into 3 segments. So once we found our critical values, it broke it up into segment A, segment B, and segment C. This is exactly what we did. So then we chose something from A, and I think we got what? Positive, right? You'll see it here. So see, if you choose something from A like -2, f prime was positive, so that means the original function is increasing on segment A. We chose something from B, we got a negative first derivative, that means the original function is decreasing on segment B. We chose something in C, the first derivative is positive, so the original function is increasing. Okay, so therefore by the first derivative test has a maximum value at when x is -1 and a minimum value when x is 2. We found the corresponding y values and then graph the function, right? We put it all together and I think we got that same image, right? So maximum value. Oh, did we not? Oh, wait a minute. Let's go back. I think we got the wrong Wi-Fi. I don't know how we got that wrong. Maybe we didn't. Let me see something. Yeah, we got that. -119 and 2, -8. Yeah, we got those. Okay. Okay, so I think we got that same thing. Wait a minute. Did I plug it into the first derivative? Oh, that's a quick check. Okay, it was irking me. It's a different example. I was like, why does it look so different, right? Because it's a different example. Okay. So I guess he didn't graph this one, but that's fine. Yeah, so this is a quick check. That's why that one looks different. Okay. So we kind of made it halfway through 3.1. I'm going to have to piggyback off of my pre-recorded lecture. So we should have gone through this in the lecture, in the recording. So, I'm going to have to piggyback off of that. And for the remainder of class, let's go ahead and hop into section 3.2. Okay. All right. Did you guys have any questions from the previous one? I feel like there should be questions. Hopefully you're not completely shut down. Just for right now, just try to listen and just kind of be present as best you can. And then take a breather, take a break, play some games, eat some food, take a nap, get some rest. And then as soon as you wake up, when your mind is fresh, give this a go. And work together. Hopefully you guys are working with the tutors. I do have some people that email me and we kind of go back and forth. A lot of times we'll answer the questions here. But the main thing is that the first derivative is telling us whether the original function is increasing or decreasing. Okay. So now what we want to do for section 3.2 is using the second derivative to find max and min values in sketch curves, right? So the first derivative tells us whether the original function is increasing or decreasing. Let's see, what does the second derivative tell us about our original function? So then we're asked to classify the relative extrema of a function using the second derivative test and then graph a continuous function in a manner that shows concavity. Okay, so suppose that f is a function whose derivative f prime exists at every point in an open interval, I. Then f is concave up on I if f prime is increasing over I, right? F is concave down on I if f prime is decreasing over I. So concavity is like it's concave up, like you think about like a cup, right? The cup is curving upward or opening upward. Concave down is like the cup is opening downward, right? And that's essentially what the second derivative is telling us. For right now, we're only looking at whether the first derivative is increasing or decreasing. Let's see this in action. So if f double prime is positive on the interval, wait a minute, where's my, okay, so let me back up right here. I don't know why it does it. Okay. So if f double prime is positive on the open interval I, then the graph of f is concave up. That is that f prime is increasing, so f is turning up on I, right? F double prime is negative on the open interval, then the graph is concave down. That means f prime is decreasing, so f is turning down. All right. Long story short, when the second derivative is positive, that means the original function is concave up on that interval. When the second derivative is negative, that means the original function is concave down. Right, and so like how we had critical values where the function went from increasing to decreasing, we also have critical values here where the function goes from concave up to concave down or vice versa. Okay, let's see. So suppose that f is differentiable on an open interval and there's a critical value c on this open interval where f prime is zero, then f of c is a relative minimum if the second derivative is positive. F of c is a relative max if if the second derivative of c is negative, right? So say we get our critical values from the first derivative test, then we can take that same critical value and pass it through the second derivative. So when we take that critical value and evaluate it in the second derivative, if we get a positive result, that means it's concave up, which means that that critical value is a relative minimum, right? It's going to be the bottom of a valley. If that critical value is positive in the second derivative, I think I said it backwards. I think I'm repeating it. If the second derivative is, if that critical value is negative in the second derivative, that means it's concave down. That means we have a relative max, right? So that's, it sounds like a lot. It's not as bad as it seems, right? And so what we're saying is we get a critical value. Instead of doing the first derivative test to determine whether it's a relative max or min, you can pass it through the second derivative, and that also will tell you whether it's a max or min. Okay. Where the second derivative is 0, then we have to use the first derivative test to determine whether it's a relative extrema, right? We can't always, sometimes we can't even use the second derivative to evaluate, so then we default back to the first derivative. But sometimes it's easier to use the second derivative to test, and sometimes it's easier to use the first derivative, right? So we're doing the best we can to seek out simplicity. Let me change this view to seamless, and let me give myself 2 pages. Add a page, and let's add a page. Okay. All right. So right here. Give me just a second. I want to go ahead and load a copy of the previous section before I forget. Let me share. I'm gonna send it to Box. Let's see. Spring calculus notes. Ouch. Handwritten. That's good there. Yeah, you can send it there. Okay. So at least you'll get a copy from 3.1 of the instructor version. Come on. Okay, and then let's go back. And we're working on 3.2. Okay. So we're asked to graph the function given by this and find the relative extrema. Okay. So let's do a brief summary again like we did in the previous section. Okay. So when sketching these curves, the first thing I like to do again are investigate my intercepts as best I can. Okay. So I like to start with the y-intercept and then investigate the x-intercept. Okay. Next, let's do the first derivative test. First derivative test. Okay. And that's going to tell us whether the original function is either, we're going to say increasing or decreasing. Okay. Then third, let's look at the second derivative test. That tells us about concavity. Right, whether the original function is concave up and concave down. The critical points for the second derivative, we call those points of inflection or inflection points. That's where the curve goes from concave up to concave down. Okay. 4, find a few additional points. Between and beyond all critical values and x-intercepts. I'm going to say between and beyond all critical values and x-intercepts. Okay. And then 5, you put it all together. So graph. Okay. So the only difference here, we just added the second derivative test. That tells us about concavity. Okay, let's give it a go. We don't have much time. We're not going to be here much longer. So just hang tight. You know, I do acknowledge it's a little bit overwhelming. It can very easily be. I'm not saying it is for you, but you know, I know that it is. Just hang tight. Just listen for now. Just, you know, like a conversation. And then when we're done, just shut it all down, rest, get some, eat some food, rest. And then when you wake up, try it again. If you're not feeling it, step away from it for a while and then keep knocking at the door and it will open. All right. Okay. So let's go f of x cubed plus 3x squared minus 9x minus 13. Okay. This is looking like similar deal with the x-intercept, but we're going to let that be for now. So first, let's investigate our intercepts as best we can. Okay. And again, I like to start with the y-intercept. Okay. So for the y-intercept, if we set x to 0, 0 cubed, 3 times 0 squared, 9 times 0. Ultimately, we just get negative 13. Okay. So the y-intercept we get was 0, comma, negative 13. Okay. X-intercept, if we set y to 0, I was already thinking about the factoring. We get an x plus 3. So I'm just going to leave it because it's looking kind of funky. So I'm just going to kind of skip the x-intercept for right now like I did the previous one. So then let's go on to the second part. Let's look at our derivatives, right? So let's look at f prime. Okay. So the first derivative is going to be, in this case, 3x squared plus 6x minus 9, okay? And then what we want to do is set this to 0 and solve, okay? If we set this to 0 and solve, basically we're looking for a critical value. So we want to find out where either the first derivative is either 0 or where it's undefined. Again, because this is a polynomial, it'll never be undefined. So we want to see when is this going to be 0. We can factor out 3 from all of these terms. So I'm just going to divide every term by 3, and we're going to have x squared plus 2x minus 3 equals 0. And then if we factor that guy, we get x and x, one's a plus and one's a minus, a positive 3 and a negative 1. Okay. So from there, our candidates for our critical values are going to be negative 3 and 1. Okay. So from there, okay, I'm going to kind of skip the first derivative test because I just want to showcase the second derivative test, right? We could do the first derivative. We're going to come back to that. So for right now, I want to look at the second derivative. So our second derivative, if we just take the derivative again, we're going to get 6x plus 6. Again, we want to set that to 0 and solve. Okay. So what? Subtract and divide. X equals negative 1. Okay. Okay. So let's take these piece of information and let's plot these on the number line. Okay. So we have negative 3, we have negative 1, and we have 1. Right? I just put them on the number line. Okay. So with the first derivative, negative 3 and 1 are going to be 0 in the first derivative. Okay. I'm going to come back to the first derivative test. I want to go ahead and look at the second derivative, right? So if we plug in negative 3, now the negative 1 is 0 in the second derivative. When x is negative 3 into the second derivative, what is this? This is going to be a negative 18 plus 6 is ultimately going to be negative. So the second derivative is negative here. So that means our original graph should be concave down, which means that this should be a relative max. Right? We need to find the corresponding y. Okay? Because again, the critical value when x was negative 3, when we put it in the second derivative, we got a negative result. So that means that the original function should be concave down. So then there's a good chance that that's a relative max. Okay. The second derivative is 0 at negative 1, and then we plug 1 into the second derivative, we get a positive result, which means the original function is concave up, right? So that confirms that negative 1 is an inflection point. That's where the graph goes from concave down to concave up. This second derivative being positive implies that this is a relative minimum at this x value. Okay. So then it's probably a good idea. Let's go ahead and if we put negative, okay. So when x is negative 3, if we're saying that's a maximum value, and when x is 1, that's a minimum value, then what can you anticipate? Should the graph be increasing or decreasing between negative 3 and 1? If we're going from, for it to be a max, that means we're going from increasing to decreasing. For it to be a minimum, we should be going from decreasing to increasing. So long story short, when we plug in -1 into the first derivative, we should get a negative result. Let's just confirm that. If we plug -1 into the first derivative, let's see. This is positive. This is negative. A positive times a negative is negative, right? So the first derivative of this guy is negative, which implies that our original function is decreasing there. We could choose a point to the left of -3 to confirm that it's increasing over here. And we should choose a point to the right of 1 to confirm that it's increasing there, right? We need to pass us through the first derivative. Like, okay, if we plug in -4, this is negative, double negative is positive. You see the positive here because that means it's going to be increasing. If we choose something to the right of 1, like 2, this is positive, a positive times a positive is positive, okay? So again, the first derivative tells us whether the original function is increasing or decreasing. The second derivative tells us whether the original function is concave up or concave down, okay? So now let's put all this together. We need a few additional points between and beyond our critical values. All right, so I'm gonna say that was, let's see. So 4 few additional points. Okay, a few additional points. So I don't think we found our x-intercept here. We got our y-intercept was 0, -13. Okay. So let's find the corresponding y value. So let me see. We're gonna choose. Let's choose when x is. Let's do when x is -4. Let's do when x is -3. Let's do when x is -2. Let's do when x is -1. We might be doing a little bit extra. I mean, we should do something. Okay, we can, yeah, a point between -1 and 1. Let's do when x is 0. And then let's do when x is 2, right? So we just chose all these x values. We're going to find the corresponding y value the same way we did before, but basically just passing these x values through the function. We could just look at the table on the calculator as well. That would work as well. Matter of fact, let's do that this time. I'm trying to wrap this up to get you guys out of here. We're going to go ahead and let this be the end of the day. We just need to finish this guy. Okay, let's go here. The original. Right there. Okay, we got x to the power of 3 plus 3x squared minus 9x. That's not an x. Minus 13. That's the original. Okay. Let's go to the table. So let's go table set. We want the table to start at -4 and change by 1. Let's hit enter. I'm going to hit second graph to activate table. Okay, so we have the corresponding y's. So when x is -4, we get 7. When x is -3, we get 14. When x is -2, we get 9. When x is -1, we get -2. When x is 0, we get -13. And when x is 2, we got -11. Okay. So I just chose x values that were between and beyond all of our critical values. Okay, let me see. The original is a cubic function. Okay. So let's put all this together. We go to view, templates. I want my same dots. That looks good. Let's apply. Okay. My x's look like they go from about -4 to 4. My y values, let's go -20 to 20. Okay. So we'll let this be our x-axis. Positive y is like this. Okay. All right. About there looks good. Okay, so let's plot these points. So let's label this. We said -4. That was a weird sound. I know we're about to wrap up. Hopefully my device survives for me to finish this without me having to plug in. If it cuts out, then that's gonna be in the class. But let me try to wrap it up. Let me see. 1, 2, 3, 4. Let's go like this. This will be our 1, 2. No, that's too big. 1, 2, 3. 4 is there. Okay. And the same thing here. 1, 2. I might be spacing this out too much. 3 and 4 is there. Okay. Let's label this. This is the origin. We said this is our 1, 2, 3, 4. 3, 4. These guys are negative. Okay. The y values, we said 20 to 20. Let's see if we go 5, 10, 15, 20. 5, 10, 15, 20. Okay. Okay. So now if we plot these points, -4, 7. So 7 is about here. This is -4, 7. Okay. -3, 14. So 14 is about here. We said that was our max. Okay. So this was our relative max here. -2, 9. 9 is there. So about there. This was just an additional point, -2, 9. Okay. -1, -2. So now we see the zero somewhere between -2 and -1. But -1, -2 is about here. Okay. 0, -13 is here. Okay. 2, -11 is about here. What was our minimum when x was 1? I always skip that for some reason. Let me go ahead and let me plot the point when x is 1. It should be here. When x is 1, we got -18. -18. I don't know why I was missed out. So 1, -18 is here. Let me move this label. There's good. About there's good. Okay. And this was 1, -18. I know. I'm trying to wrap up. I'm trying to get these guys out of here. 1, -18. Okay. And then a smooth curve. So, and it does look like it kind of goes down over there. I just added space through that one, through that point, through that point, through that point, that point. And we could find some more, and it should continue that pattern like that. Okay. So like this. Oh, it's going to be close, guys. Where I could easily just plug in my device, but that's too much like right? Got to have a little bit of thrill, right? So when we did it by hand, we got this. Let me go to view, single page. Okay. Something along those lines. Okay. And let me label this really quickly. Relative min. Okay. Let me go ahead. Let me just do a quick check. Okay, critical values of max and min, and I think we get the same image, right? We could have chosen when x was 3 and a few other points, but okay. All right. So I don't really want to do much more than that, and my device is about to die. Did you guys have any questions before we go our separate ways? So, I mean, you got your work cut out for you, but it's doable. Just take a deep breath, know that you can do it, ask questions, work together, work with the tutors, like it's okay. and just you get unlimited attempts. I'm not trying to go hard. I'm really just trying to expose you to these concepts and encourage you to like try. I'm not trying to like slam hard or anything like that. Okay. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Okay. Take care. Peace.
Sir. Professor C.
Yes.
Yeah, I had one question. I had emailed you a couple of times, but I need to redo, or I have to do the work from like the past week because I haven't been able to get the textbook.
It's not a book. It's just on Pearson.
Yeah,
So,
I haven't been able to get that. Like
and it's available. The late penalty is going to hold, but it's only 10%. So any assignment that you still want an A on, you can still earn it. It's just like, you'd have to get a perfect score to get that 90. And students do it all the time. But yeah, every assignment is an unlimited attempts. There's only a 10% late penalty, even the exams. So if you took exam 1 and you made below a 90, you can still improve your score. This is for anybody.
okay.
Okay. So,
All right.
Yep. I ended up plugging in my device. Anybody else have questions before we go separate ways? Going once, going twice. All right, guys. So yeah, just keep emailing. I struggle with responding to emails, but if I don't respond, just ask me next class. Like that's the long and short of that. Just ask me. You have to just kind of remind me. Okay, guys. All right. Enjoy your evening. I'll see you Wednesday. Wednesday, next 2 sections. So 3-3 and 3-4. All right. So, next two sections, 3-3 and 3-4. Okay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys, or your evening. Take care. Peace.
Bye, Professor.